Good. Now, don't feel ashamed of reminding me of that. Okay, sometimes I forget. So what we are going to do today, again, just summarizing everything, so it gets recorded there. We are going to cover capacitors in series and parallel. Just as a reminder, I corrected your exam 1 grade. Instead of 27 points, now it's 26 points. As a result, your grade went a little bit higher. We have a quiz today at the end of the class. We're going to finish the chapter on electric circuits. And first, we're going to start with capacitors in series and parallel. Okay? So here you go. We start with those two capacitors separately. We can buy those things out there in electronic stores. And we can connect capacitors in series, either in series or in parallel. I talked to you about capacitors, but I didn't tell you how we connect them. What happens when you connect them in series and in parallel? You already know that when you connect a resistor in series, you sum the resistance, R1 plus R2. 3 resistors in series, R1 plus R2 plus R3 is the equivalent resistance, right? Capacitors is going to be something a little bit different. But let me walk you through exactly what happened when we charge the capacitor, right? When we charge those two capacitors that are now connected in series, what's going to happen? The plate of the capacitor that is facing the positive side of the battery is going to become positively charged. Why is that? Well, the reason is very simple. That's a very good, simple model that's very easy to understand. Think about those charges here in the plate of your battery that can move freely through this conductor. The wiring, the copper wiring that goes from the battery to the capacitor, okay? So it is as though those positive charges are flowing through this wire and accumulate here in the plate of the capacitor. That's what happened. The same thing happens with the negative charges, okay? The negative charges flow from this negative plate and accumulate in the other plate of the capacitor. And I'm going to do that just like a movie, right? That's the first thing that you have to know. Oh, this one. Okay. In the next step, what's going to happen? In the next step, those positive charges that are here in this plate, okay, are going to attract the negative charges in this plate here. Don't forget, we have a dielectric here. We have an air or vacuum or some other dielectric material. Because of this dielectric material here in between, the positive charges cannot jump to the other plate of the capacitor, okay? And when these positive charges attract the negative charges on that plate, okay, then the other plate becomes negatively charged. Now we have a capacitor that's charged, positive on one side, negative of the other. But the same happens to these other negative charges that here in the other plate is going to attract the positive charges. At the same time, those negative charges are going to repel the other negative charges, okay? So not only you have the attraction from this positive charges in the capacitor, but they are going to have also the repulsion of those negative charges that populate the other capacitor. The same story goes for this guy. And now we have a capacitor that has a capacitance C1, right? Before I connected the battery, there was no charge to those capacitors. Remember that? It was discharged. When I connected, now we have a charge, Q, and an electric potential between those two plates. This plate is going to have, I'm going to say that it's going to have a electric potential V1, and this other plate is going to have an electric potential V2. Okay? What you have to memorize is very simple. When you have capacitors connected in series, the charge is in this capacitor is going to be the same as the charge in the other capacitor. Okay? That's what you have to memorize. However, the electric potential is going to be different. Okay, the electric potential is going to be different because now the capacitors are in series, and this electric potential V1 here plus V2 is going to be equal to the electric potential provided by the battery. Those are the things that you have to memorize for, but it's, you know, it's logical. Okay, it is logical. It is logical because this battery can provide only so much electric charges to each of those plates. So that you must have equal amount of charges here in those two capacitors. And also because of conservation of energy, the principle of conservation of energy, you must have that electric potential difference between this plate and those two plates. Whenever they are summed, they must be equal to the electric potential provided by the battery. Energy provided by the battery is energy in the first capacitor plus energy in the second capacitor, whenever they are in series. Whenever they are in parallel, the story changed, right? And that's exactly also what happens with resistors. Going back, resistors connected in series behaves in the same way. And then you have to go back to that table that I drew for you. Let's blow up. That unfinished table. Like that. Okay. Here, what you have here, both for resistors and capacitors. The voltage behaves in the same way for resistors and capacitors. Okay. In the case of the current, it applies only to resistors. Here, for capacitors, it's not the current. It's something else that's close to the current. Okay. It is the charge of the capacitor. And instead of having I1 equal to I2 equal to IN, we are going to have Q1 equal to Q2 equal to Qn, all the way down to Qn. It's supposed to be an equal sign here, not a plus sign. Right? Supposed to be equal sign here. And here too is supposed to be an equal sign. And we're going to, can you remember that? If you remember that the current is the same for resistors, you will also remember that the electric charge is going to be the same in capacitors. 1, 2, 3, 4, 5, all the way up to N is the number, the capacitor number. Capacitor 1, capacitor 2, capacitor 3, and so on. Okay. And okay, that's what you have here. What's going to be the equivalent capacitance in this case? Okay, that's the question that I make for you. What is going to be the equivalent capacitance? Once we combine those two capacitors, what is going to be the equivalent capacitance of those two combined capacitors? Just like we combine the resistor, right? And that's an interesting, thing that you're going to see for capacitor. It doesn't behave exactly like a resistor, right? I'm going to do a, okay, let's see if I can do another table for resistors in series. Remember what happened to resistors in series. I'm going to do the same here. Resistors. One more student coming. And resistors. And okay. Yeah, okay. Resistors. And resistors in series. You already, is going to be R1 plus R2 plus Rn equal to your equivalent resistance. And here is going to be different. It's going to be a similar equation, but it's going to be raised to the power of -1. Okay, here you go. Good. R1, 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 R-1, right? And the equivalent resistance is going to be raised to the -1 as well, n resistors. And then we are going to repeat for n capacitors. We don't need that. N capacitors. Okay, I'm gonna save this one for now. We can prove that mathematically, just like we proved for resistors, okay, and capacitors. How do you do that? Okay, we use the information that we have for the voltage, okay, and the definition of capacitance. Let me get this one here. Let's see. Yeah, let me get that. Okay. For capacitors and resistors, we have V1 plus V2 plus V3, so on, right? Let's do only 2, right? So we don't have to mess up with equal to V. Goes like that. V1 plus V2 equal to V. And then we can extend for N. For capacitors and resistors connected in series, we have, okay, for resistors, we and with capacitors and resistors connected in series, we have I1 equal to I2. Consider two of each, right? Connected separately, okay? Separately in series, okay? One circuit containing 2 resistors connected in series, and another circuit containing 2 capacitors connected in series. We have, and okay, should be equal here. Series Q1 equal to Q2 equal to Q. Okay, like that. Here's for capacitors. Remember. Here's for resistors. Here's resistors and capacitors. Capacitor. Apply to resistors and capacitors. Yeah. Okay, good. So now we have that. Okay, we have that. And what I'm going to do now, I'm going to use this equation here. to derive what happens whenever you connect the resistors in series, right? Resistors in series, V1 can be rewritten as R1I, right? And R2I. Make sense? Right? That's for resistors. We didn't derive that, right? I just told you what was the result at that time. Okay, so going back, we're doing for two resistors in series. Yeah, here you go. Two resistors, R1, the V1 here is going to be R1I using Ohm's law, and R2I. Okay, but when we combine those two resistors, you're going to have an equivalent resistance. I'm going to point out that what we still do not know what's the relationship between the R1 and R2. We're going to have equivalent resistance. So it is the same as stating as that V that you see right in here is going to be the equivalent resistance times I, okay? And now what you see right in here, you can also apply the Ohm's law. We can also apply Ohm's law. Now you can see that this I here is going to cancel out this I here, all those three I's, okay? And we obtain that the equivalent resistance is going to be equal to R1 plus R2 whenever you have only two resistors. Okay, I proved that for you. Last time I just told you, equivalent resistance of resistors in series was equal to R1, R2 plus R3, and so on, right? What about for capacitance? For capacitors, we do the same. But remember, if V equal to Ri for resistors, V is not going to be Ri for capacitors. Remember that, right? For capacitors, is not V equal to Ri. We have. Okay. For capacitors, we use that definition of capacitance. Okay. And what's the definition of capacitance? C1 is going to be equal to Q1 divided by V1, right? That's what it is. And we have the same for C2. We go there, the definition of capacitance. Okay? But don't forget that because the capacitors are connected in series, Q1 is going to be equal to Q2. Right? Here you go. Equal to Q2. It's going to be equal to Q. Compare this relationship with Ohm's law. Ohm's law is different. Okay? And I'm going to see exactly how different it is. And I'm going to even write down in that table so you can see it side by side. Okay? In Ohm's law, V1, right, is equal. And I'm going to rewrite this law is slightly different. So you can see the difference between Ohm's law and the definition of capacitance. Okay, here I wrote the capacitance in terms of Q and V. Here I'm going to write the resistance in terms of I and V as well. R1 is going to be equal to V1 divided by I, like that. We see what's happening here? Whereas the resistance is directly proportional to the voltage, in the capacitance is inversely proportional to the voltage. Because of this important difference, the equations for capacitor, the equivalent capacitance of capacitors connected in series is going to be different than the equations for the resistors, for the equivalent resistance for resistors connected in series as well. Okay, let's continue with that so you can understand what's going to happen. Okay, what I'm going to do, I'm going to get those two equations here, and here write it in terms of V1. V1 on one side, capacitance on the other side downstairs, right? When we wrote again Ohm's law, the resistance was multiplying the current. In this case, the capacitance is dividing the charge, the electric charge. Okay, and we can repeat that. V2. Okay, like that. And now we can substitute those two equations in this other equation right here. And then, oh, and don't forget, because we're looking for the equivalent capacitance, right? I'm gonna change the position of those guys here so I don't have to keep on shifting back and forth. I'm gonna copy. Good. And paste there after the resistors. I'm gonna paste right in here. Okay. C1, C2, okay. And then you're gonna have an equivalent capacitance. You can also call that C12. So this circuit here is equivalent to this circuit here. Because now the equivalent capacitance has a voltage of equal to V due to the conservation of energy. We can also write that V is going to be given by C time by Q divided by the equivalent capacitance. And then we substitute that right here, okay, in this equation. V1, we get something similar. Similar, not a similar equation, but a similar in terms of cancellation, right? See that? The Q's here cancel out. And we have that the equivalent capacitance of capacitors, the inverse of the equivalent capacitance is equal to the sum of the inverse of the capacitance of the other capacitors. Okay. And now I can go ahead and write that down here. In capacitors connected in series is going to be just like that. And the reason for that has to do with the fact, has to do with Ohm's law. Let me change here C to the power of -1, right? Like that in capacitors. And now we have to do for capacitors connected in parallel and resistors connected in parallel as well. Okay. At this point, you should already have guessed that when capacitors are connected in parallel, the equivalent capacitance are going to have the formula for the equivalent capacitance is going to have the same format as this one, and I'm going to prove that for you mathematically. Go. C2, Cn. Okay. And I'm going to I'm not going to need this one here, but I'm going to need a row here. Resistors. Let's see, how am I going to do that? Resistors. I think I'm going to need another one. Yeah, resistors, capacitors, and then elements, right? Elements. Here, relation, mathematical relation. Here is going to be V equal to Ri, or even better, R equal to V divided by I. And here is going to be C equal to Q divided by V. Note, see the important difference, okay? Remember also that the current is related to the charge, right? Delta Q over current is delta Q over delta T. Okay, I'm going to italicize here, so it looks good. And I'm going to boldface the V here, so you see why. Okay, why we have this difference in the equivalent capacitance and equivalent resistance. Okay, so now let's do for capacitors, for resistors, separated in series. Okay, so now I'm going to repeat that for parallel. Okay, for capacitors and resistors connected separately in parallel, we have what? We have the inverse, right? We're going to have V1 equal to V2 equal to V, applies to resistors and capacitors. Here applies just to the current and for resistors, and here applies just for the charge. Okay. Okay, don't forget now that the current is different, because, okay, let's go back to the drawing so you can understand why we have a difference here in current. We're gonna do this for two resistors. Let's see here. Okay, here you go. Okay, the current comes out, here's negative, comes out from the negative to the positive. It's fed here, that's the main current. When it gets to this junction, just like cars at a junction in the freeway, some of the cars go to the left lane, some of the cars goes to the right lane, right? Here the charges do the same thing. Some of the charges goes to this left lane here. Some of the charge goes to this other lane here, this straight lane, I1 and I2. Because of conservation of charge, I1 plus I2 must be equal to I. That's why you got that. Furthermore, because the resistors are connected in parallel, the electric potential between those two ends, electrical potential energy between those two ends must be the same between those two, electric potential difference, right? That's why I put V2 equal to V. And that's what we have here, resistors and capacitors. V1 is no longer V1, but it's going to be V. Okay. R1 is V divided by I1. And even better, we are going okay, and what are we going to have now? We are going to have, here we have to use this equation now, not the voltage equation. Okay, we have to use this one here for resistors. We use the voltage for the other case. I1 is equal to V over R1. Okay, and we substitute right here. Okay, we get this one right here. The R2. Okay, and that's the V over what? The equivalent resistance, right? Remember that? Going back to parallel. This circuit here is similar to this other circuit here. So the current flowing through this equivalent resistor is going to be V divided by R. And now you can see where that relation for resistors in parallel comes from, right? Go. This V cancels out, and we have that relation that I wrote before. And now we are going to repeat that for capacitors. We're going to repeat that for capacitors, but we're not going to use V like we used before. We're going to use Q. Okay, just like we use I for the resistors. For capacitors, we have that relation here. All right, Q1 plus Q2 equal to Q. Now, the voltage is going to be the same because the capacitors are in parallel, and I can here write my Q as C1V, my Q1 as C1V. And we do observe that in real life, right? So here you go. I'm gonna repeat just for Q2 now, so I don't have to do the derivation. Okay, like that. Use the summation. Here is gonna be Q1 plus Q2 equal to Q. Okay. Replace that right in here for Q1 and Q2. And do not forget that we are going to have here on the side, we are going to also going back to that drawing, right? For the capacitors in parallel. I don't have a drawing for capacitors in parallel, unfortunately. Yeah, I didn't do it. But those two capacitors in parallel is going to have a capacitance that's going to be equal to C equivalent times V, right? And again, you can see why we get the equivalent capacitance of capacitors in parallel being equal to C1 plus C2. Okay, that's what we have for capacitors that I want to cover. Now it's just a matter of doing some problems, right? Just like before, just like for resistors, okay? Okay. Just like for resistors, if capacitors are connected in parallel, okay, if capacitors, just like before, let's put it this way, just like before, if capacitors, if resistors, right? I'll put that here, are connected in series, okay, their equivalent capacitance, their equivalent resistance is going to be the sum of each capacitor, resistor. Okay. What does it mean? It means that the equivalent capacitance, equivalent resistance is going to have a value that is higher than the highest capacitance. Resistance, right? And then you have the opposite for resistances or capacitors connected in series, right? Equivalent capacitance is going to be the sum of the inverse of the capacitance. Capacitance should be like a resistance, not resistor, but resistance. Here too, right? The equivalent capacitance is going to be the sum of each capacitance. Resistance. The consequence is that the equivalent capacitance is going to have a value that's higher than the highest capacitance value slash resistance value. Here is all the way around. It's going to have the sum, it's going to be the sum of the inverse of the capacitance. This means that the equivalent capacitance is going to have a value that is lower than right? Then the lowest capacitance resistance of the set, right? Of the set. The lowest capacitance value lower than the lowest capacitance value of the set. Of the set of device, of the set of devices, right? Of the set of elements, devices. Okay, so we go in a mathematical sense, right? Let's see if I can do a table too. Tables are very useful. Let's see here. Maybe I can. Yeah, let's see if I can use this one here. Okay, let resistors R1 resistors R1 greater than R2 greater than Rn, right? Okay, equivalent resistance is going to be larger than the, let's see how I'm going to do that. Equivalent resistance is going to be greater than the highest resistance value, right? Here's the same thing. We go. Capacitance 1 greater than capacitance 2, and capacitance n is the smallest of every one. What does it mean? It means that the equivalent capacitance is going to be smaller than the smallest capacitance value. Okay, that's for series. For parallel is the contrary. And here we are gonna get, let's see here. Remember, C1 is the highest capacitance. Okay. Like that. Lowest value, right? Highest value. Save that here. And now we can move on. What time is that? 9:44. Get some water here. Any questions? Then all you have to do is to figure out how to apply that in circuits, right? That have a mixture of capacitors that are in series and parallel. Okay. It's 9:45. Now I think we can have our break now. And break from 9:45 to 10 o'clock. Oh, before we go to the break, right? Okay, let's take attendance. It's not going to be 9:45. It's going to be maybe 9:50 or 5. Back to attendance. Today is the 13th. Randy Bautista. Let's see. Randy, I see Randy here, but I don't hear from him. I'll put a star for Randy. Vanessa Bonilla. Good. Okay, Randy just answered. Thank you, Randy. Okay, and Vanessa, Ashley Diaz. Are you there, Ashley? I don't see Ashley here in my list. Next is Natalie Espinosa.
Here.
Thank you, Natalie. Jeanette Garcia. I see Jeanette. Okay.
I'm here.
Okay, Jeanette. Okay, thank you. Noor Hassan. Are you there, Noor? Okay, I don't hear from Noor. Let's go for the next one. Blanca Hernandez.
Here.
Thank you, Blanca. Kaylee Hernandez.
Here.
Thank you, Kaylee. Joshua Jimenez. I don't see Joshua here in my list. Randy. Alondra Lima.
Present.
Okay, thank you. Kennedy.
Here.
You. Daisy Mariscal. Thank you, Daisy. Next is Yesenia. Hi, Yesenia. I need you to type that in the chat box. Thank you. Ryan Ong. Okay, thank you, Ryan. Okay, Randy already gave you attendance here. Am I sharing the screen? Yes, right? You can see, right, the spreadsheet. Artur,
Yes.
okay, thank you. Artur Pacheco. Okay, yeah, okay, thank you, Noor. And Artur Pacheco, let's see here. I don't see Artur Pacheco here in my list. Label it. Okay, Label, are you there? Okay, I don't hear from Label, but she's in my list. Next is Donia.
Here.
Thank you. Next, Elika.
Here.
Thank you. Brianna Valencia. Thank you, Brianna, and Justena. Thank you. So we have a summation here that equal to 16. Okay, good. Let's see. Late Blue, are you there? One more chance.
Professor, I'm here. I don't know if you got the direct message.
Who's that?
Randy?
Yeah, you're Randy. Yeah, I gave
perfect, thank you.
I gave you attendance, okay? Just label that. Okay, so let's leave it this way. It's 9:50 right now. We can go ahead and have our break. And I see you in 15 minutes. I am back here. And that's okay. So let's take a look here. Chapter 20. Electric circuits, 1, 2, 3. Okay, we're going to do electric power now. We did, let's electric power right in here. Okay, and okay, every time that we are building a circuit with a resistor, okay, we want to find out how much energy that the circuit spends, okay? And in order to have an idea of how much, what is the battery that we are going to use and how long that battery is going to last in the circuit, we must know what's the electric power of that circuit, okay? So that's what we have right in here. Is a way for you to estimate how long your battery is going to last in your circuit. Okay, and there is a very simple way of deriving the formula for that. So we're going to do that, electric power. And let's get our list of sections that we covered. The section is very long, you know, they include lots of things that we usually include in more than one chapter in a regular physics course, and it would not part of temperature of temperature dependence, right? We close this one. 1 to 22, 23, okay, we're doing 24 now. We didn't do 20.5, series wiring, parallel wiring, 8. We're not going to do internal resistance. And then we certainly have to do this one. We did 2012. We didn't do RC circuits yet, okay? So let's go back now to 20.4. Okay, electric power. Electric power. And what else do we want to do? You know, we First we have to do Kirchhoff's rule. Kirchhoff's rule. Kirchhoff's rule, which is 20.10. And internal resistance. You already know more or less how to measure current and voltage, okay? And that's something that we cover in the lab, so I'm not going to cover here in the lecture. And capacitors inserted in parallel we covered, and so let's finish this chapter is 20.13 RC circuits. But right now, let's do electric power. So electric power. When you build a circuit, you need to know how much power it is going to spend. So you can have the right power source for the circuit. Okay. Remember batteries, for instance, batteries and capacitors. Batteries and capacitors, they have so much energy stored in them. Okay. So if your circuit is has a very high power, your battery may not last very long. Your capacitors also may not last the period that you want it to last. Okay, that's why we cover this chapter on electric power. Okay, if you know how much joules per second a given circuit is spent, and you know that a given battery has so much joules, or in electrical parlance, kilowatt hour. Okay, kilowatt hour. That's what comes in your bill, electrical bill. Then you can figure out, you can estimate how long your power source is going to last in that circuit, or if it will be capable also of providing that power that the circuit is spending. Okay, so batteries and capacitors, they have so much energy stored in them. If you know how much power your circuit spends, then you can estimate how long your battery is going to last before you need to replace it or fully charge it. Okay, and that's what I was doing some time ago. Okay, I want to leave my experiment running for a long time. It was back in 2011. I was performing experiments with my devices, and what I want to do, I want my experiment to run for 9 hours, right? Very soon I figured out what was the consumption, the power consumption of my circuit, okay? And very soon I figured out that those regular 9-volt batteries that we buy out there, it was not going to last very long. It would last only 2 hours. So what did I do? Well, I went to this auto store. I bought a battery, 12-volt battery, connected my experiment to that 12-volt battery, and because those 12-volt batteries store far more energy than those 9-volt cells, I was able to run my experiment for 9-10 hours. Okay, so I would leave my experiment overnight. I would be sleeping there, and my device would keep on collecting data, so I could analyze the following day. That's very important to know how to automate experiments. And that's what I did back in 2011. Okay. And how do you calculate the power of a circuit, right? There's a way. There's a way to do that. Just remember, going back to our teachings of physics 37, the power of a given device is going to be the potential energy divided by time. Remember that? Joules per second. Joules per second is the unit of watt. The same relation applies to electrical circuits with one important difference. With one important difference. This delta U here is going to be the electric potential energy. Okay, and it can be written as delta V over, delta Q. Okay, remember? It's V over Q, right? We can write like that too. Delta V, let's see. No, it's all the way around, sorry. Is delta Q times delta V, right? It is delta V. Remember that definition of delta V, electric potential. Electric potential is delta U over, we can write down as delta Q as well. Okay. So when you solve for delta U, you get something like that. And then, what you end up having, you can write like this way. In a circuit, in an electric circuit, your delta V usually remains constant. Okay. And what changes is the flow of electric charge across a cross-section of your circuit. And then what you end up having here is the current. Okay. To simplify our notation, we are going to write, instead of delta V, we are going to write just V, which, by the way, is the electric potential difference across a resistor. Okay. Using Ohm's law, if this circuit uses ohmic elements means elements that obey Ohm's law, not every circuit element obeys Ohm's law, okay? The above relation can be written in different ways, in two different ways, in two more different ways. Okay. Okay, one of them is V equal to Ri. So you replace that right here. And you get Ri squared. Ri squared, that's another equation. Okay. ID, Ri, and then we can have another way. Let's see, which other way can you do that? So P equal to VI, right? P is also equal to Ri squared. And there is one more equation. Try to figure out another relation that we can get. I'll give you a little bit of pause here so you can try to figure out how you can derive a third equation. Yeah, RR squared. Okay, so what did I do? First, I substitute for V, right? And I got this equation here. There's a way to find the other relation, and instead of substituting for V, you substitute for I, right? And let's see what happens. Right? Use this equation. He write Ohm's law in terms of the current. Which is V divided by R. Substitute right in here. And you get a third relation, which is going to provide you with exactly the same numerical result than the other equations. Okay? 3 ways of writing the power of a ohmic circuit. A circuit that uses ohmic elements. VI, RI square, and V square over R. Okay. 3 different ways. We have an example 5 in the book. We're going to do this example so you can have a better idea how that works, okay? How this equation works. We have a flashlight. We have a flashlight with current 0.40 amperes, and powered by a 3-volt battery. Find the power delivered to the bulb by the battery. Remember, that's the source of energy here. And B, the energy dissipated in the bulb in 5.5 minutes. Okay? By the bulb. No, stated by the bulb. So those light sources that we have, they put out heat, right? And this is the energy that the light source is dissipating. Even LEDs, they put out heat out there, but they put out far less heat than the regular incandescent light bulb. This flashlight that we're talking about is an incandescent light bulb. So solution, right? Now, The battery itself has a voltage of 3 volts and input a current of 0.4 amps. Okay. Which end up being 1.2 volt times amp. This thing is supposed to have a unit of power, which is the watt. We really get unit of power there. Let's take a look. Here is joules per coulomb, right? And here is coulomb per second, right? Coulomb cancels this coulomb, and we end up with joules per second, 1.2 joules per second, which is the power provided by the battery. And by the way, joules per second is the watt. Okay, that's how much power this battery delivers to the circuit. Okay, and then we want to know how much power. That's the how much energy does the bulb dissipate in 5.5 minutes. The bulb is the only, is the only device in the circuit. Okay, so you can even come up, with the equation. We can, to find out the power dissipated by the bulb, right? We can use either this equation or the other one. Okay, 1025. So because the bulb is the only device that is in the circuit, so it is using up all the power that we have here. Let's see what's going on here. How much energy is it the bulb is using? All you have to do is to put here delta energy, right? Delta energy over delta E is going to be equal to 1.2 watts. And now in 5.5 watt minutes, it's going to dissipate a given amount of joules. 5.5 minutes. We go 5.5 minutes is equal, 1 minute is equal to 60 seconds. Okay, don't forget we have a multiplication sign there between. Let's go down. I don't see the multiplication sign here. I'm gonna put an X here. The X doesn't look nice, but multiplication sign is somewhere here. I can't find it. Oh, here you go. Good. Watts times seconds is joules, and then you do this math. 1.2 times 5.5. 5 times 60, I'm getting 396 joules. It's approximately 400, like which was the value that the book provided, 396 joules. Okay. So if you want your circuit to last 5 minutes, 5.5 minutes, you want the light bulb to provide energy during 5.5 minutes, you gotta get a battery that has this much energy stored inside it. Okay, so that's 20, going back here. One more student coming. Good. Now let's do Kirchhoff's rule. Kirchhoff's rule, that's important. It's okay. Kirchhoff's rule. Okay. Most problems involve resistors and capacitors that are connected either in series or in parallel. Most. But remember, the key word here is most. Okay? Not all. Okay. Most, not all. However, there are a few circuits out there that are important, which the elements are not connected, are connected neither in series nor in parallel. Elements are connected neither in series nor in parallel. Okay. For these types of problems, you must use a more generic technique to solve it, to solve them. Okay. This technique is called the Kirchhoff rules. Okay. Rules. It's a very simple technique. It's not difficult to learn. Okay, and let's start with an example. With a simple example like this one here that we have in the book. Okay. This one, you already know how to solve this problem because those two resistors are connected in series, right? So let's try to solve this problem here using Kirchhoff rules instead. Now, the best way to understand Kirchhoff rules is by, making an example, is by using it through an example. Okay. You already know that the current here is going to be 12 divided by 6, right? It's going to be 2 amps. Let's apply Kirchhoff rule to this very simple problem. And then we will look into other problems that are more difficult. Let's see if I can have an example here. Here is one possible problem. Okay, the circuits are still, the elements are still connected in series, but in this case here, you have 2 batteries. Okay, but then you have other types. Let's see if they have it here. Here we have 3 batteries. Yeah, they don't have one, the one that I'm having. Like maybe it's in my notes. Okay, this one right here. Okay. If you have a circuit just like that, you won't be able to identify resistors in series or in parallel here. Okay. So in this specific case, you have to use Kirchhoff Loop's law. But this is also a difficult problem because it's going to involve, let me see, 1, 2, 3, 4 equations. At least 4 equations, a system of 4 equations. 1, 2, 3. Yeah, a system of 4 equations. Okay. But let's do the other one, the simpler, the very first one that's here in this book. So you can have an idea how we can use Kirchhoff's loop law. Kirchhoff rules is just a statement of conservation of energy and conservation of charge. Keep that in mind, okay? Kirchhoff loop law uses uses the concept of conservation of energy. And here, I'm going to draw. Yeah, I'm going to get this. I'm going to draw what you have in there in your book here in my PowerPoint slide, so we can follow. Negative, yeah, but I'm going to do exactly the way it is in the book. Okay, negative and positive. Remember, I'm doing that for the simple circuit that we have out there. One of the, not the simplest, one of the simplest. Go. I'm gonna put one resistor here. There are computer programs that do that for you, okay, that we can buy and do that for you. All those drawings. In this case, I have to do all my drawings by hand. And I'm going to get another resistor. And finally, my vertical line. And I'm going to get some more space here. You know, I'll make sure you also do this drawing there in the paper so you can follow with me. It's a very good way to learn as well. A little bit larger. Okay, this one I'm going to call resistor 1. And this other one I'm going to call resistor 2. Subscript. Okay, resistor 1 and 2. Like that. So you have to visualize what's happening in this circuit here. And the way to visualize the current flowing in the clockwise direction. It goes from the negative to the positive. We say that is going from the region of lower electric potential to a region of higher electric potential energy, and pumps. And pump like that. Here's how I represent my current. Okay. It's very important that you visualize as a picture, a mental picture, or even a picture like a drawing of exactly what's happening in this circuit. You cannot see with your own eyes when you get a real circuit in front of you, but this mental picture is a very good model for what is happening at the microscopic level in your circuit, like that. Charges moving. Okay. So how Kirchhoff's law applies to this circuit? Okay, that's a simple circuit. This one is a simple circuit. Okay, so the way we work with Kirchhoff's law, For this specific circuit, all you're going to need to solve it is going to be the, we want to find the current. We do not know the current, okay? We know the resistors, we know the voltage, but we do not know the current. What we have to do, you have to come up with we have to apply conservation of energy to the circuit. And the first thing that you do is to identify loops to this circuit. Let me try it again. Here we go. This one? Strange. Okay, so here you go. Now I'm gonna put an arrow, this guy here. Let's see if I can do it. Format shapes. Yep. And beginning. No, that's not this one, is this one. Yeah, good. So see the tip of the arrow here? You draw a loop within the circuit. This circuit is very simple and we have just one loop. In general, you're going to have circuits with loops and junctions. This circuit has no junction whatsoever. Once you have chosen the direction of your loop, in this case, I chose a direction that coincides with the direction of flow of the current. It's okay to do that. It could have been okay if I had done the other way as well. And then you go ahead and you start to account for the energy in your circuit, okay? So we start here at this point where the charges, I'm even gonna put that point in there. I call that A. See, point A. You follow the path of your electric charge. Okay, this one is going to be my lowercase. I'll try to put lowercase a here. Yeah, point A. The charge is going to jump from a region of lower electric potential to a region of higher electric potential. That's why we use the symbols negative and positive. And we start writing our equations, okay? Here, from A to B, we have an increase of electric potential equal to V, okay? So picture your charge moving from A to B. He's jumping this gap within the battery. And when the charge jumps the gap, it gains an electric potential V. Okay, and going back to my drawing, following the circuit, the drawing, right? We have from A to B, my electric charge gained an electric potential V. And I'm going to emphasize that it's plus V. Okay. And then along these lengths here, we have wires that have negligible resistance. Remember, those wires here represent resistors of negligible resistance. That's why it doesn't have that zigzag pattern. Okay, so when the charge goes from B to C, it lost no electric potential energy whatsoever. Consequently, it lost no electric potential. From the electric point of view, this point here is exactly the same as this one because the particles didn't lose any electric potential whatsoever. Okay? But When we cross the resistor is going to dissipate some energy and pass the resistor. We will end up having a new point that I'm going to call C. Okay? From B to B, you didn't lose any energy. But from B to C, you did lose energy. You did lose electric potential. Consequently, we have to write another term here that's going to be minus V across the resistor 1. Can you picture that? Okay. I didn't apply Ohm's law yet. And then we are going to jump another resistor. And now in this case, it's going to be from C to D, right? And because the electric charge are going through a resistor, the electric charge is going to lose some electric potential energy. Again, V, in the case of the battery, because you went from negative to positive, you gain electric potential. That's why you have a positive here, positive sign here. V. And let's not forget that D and A are exactly the same points, right? Because the particle, so we close the loop. When we close the loop, we make the following statement. We say that all this summation is going to be equal to 0. This is a statement of conservation of energy. Electric potential is related to electric potential energy. Consequently, you must have conservation of energy. Now we're going to finish the problem. Here you go. This V across R1 is going to be what? It's going to be R1 times I. V across R2 is going to be R2 times I. I'm applying Ohm's law in this case. I know this guy. Let's simplify a little bit more. I'm going to drop this positive sign to simplify, and I'm going to put the I in evidence. I'm going to factor the I. Don't forget to change the signal here, the sign, right? What do you do not know? You know this guy, you know this guy, you know this one, but you do not know this one here. That is my unknown. One equation for a single unknown. You can solve the problem. I'm gonna multiply by -1 both sides, right? And then solve for I. The V goes to the other side with a positive sign. Okay. And we solve for the current. That's exactly what you'd expect if you were to solve this problem. Of course, using the technique of circuits of elements in series in a circuit. But now we are going to do something different. A circuit that's a little bit more complicated. Let's see if I have a drawing of one of those. Let's see. Yeah, let's do this one. Okay, let's do this one here. We start, we know V1, we know V2, we know R1, we know R2. Okay. But we cannot state whether this element is in series with this one because we have a battery in between them. Okay. If this battery were not here, we could say for sure that those two elements would be in series. Consider the circuit, find the current. And I'm going to copy that and put in the notes. Go. Example. Here it's going to be example 1, right? Example 1. Here is going to be example 2. Example 2. Given V1, V2, R1, and R2, find the current I. Find the current I. So we go through the steps of this problem, and what's that? We go ahead and choose a loop. Let's see, a loop that I call loop number 1, a clockwise loop. And then we choose the direction of the current. In this case, I chose the direction of current as being the same direction of the loop. Okay. Here are the points A, B, C, D, right? A, B, C, D. So we are going to go from point A. Let's do it again. Here you go. Here you go. Here's the circuit. Okay. Here's the circuit. We choose the direction of the loop. I'm going to put one more slide here. So, and I will take this one out. So it looks nicer now. And now I don't need this guy. Delete the slide. Okay. So start with the circuit. Find the current through the circuit. Okay. So choose the loop, the direction of your loop. In this case, we have just one loop. Choose the direction of your current. And label the points. I'm going to take out the points. But first, we do that. Yeah, this one goes before. You go loop, direction of the current, and points. And now we are ready to solve the problem. I'm going to go from A to B. We go from A to B, we gain electric potential. Solution. And that electric potential is going to be V1. Okay. We go from B to C. We lose energy because we are spending energy across this resistor. The resistor is something that spends energy. So I'm going to, just like I did before, it's going to be minus VR1. Then we are going to move from the region of higher potential to a region of lower potential of the second battery. Okay. In this specific case, it's going to be, because we're going from a region of higher potential to a region of lower potential, we're losing electric potential. We're going from the positive to the negative, so we put this negative V2. Finally, we go from point D to point A. We close the loop doing that. And again, we lose electric potential. And that electrical potential is represented by this minus VR2. Okay, and now we can continue this problem. Okay, here is going to be R1 times I. I do not know what I is yet, but I know what V1, V2, R1 and R2 are. And then we have R2I. Okay. I am going to factor Ri here in those two terms. And but let's factor it. And 53. Don't forget to change the signs, right? you solve, before you solve for I, you gotta change the signs here. Okay. Okay, and then we're gonna pass this guy to the other side. We change the signs here in this case, right? And we get a division here. We don't need the parentheses, right? So, okay. Now let's look at this equation. Let's interpret that, what's going on here. If, V1, notice that if V1 is greater than V2, oops. Okay, comma, then I is greater than 0, right? What does it mean, I greater than 0? Then I is greater than 0. What does it mean? What does it mean? Well, it means that we choose the proper direction of the current, okay? And the current really flows on the counterclockwise direction. There's another interpretation for that too. Because V1 is greater than V2, it means that this battery here is more powerful than this battery. And it will be able to prevail in the direction of the charges. Make sense? Okay? That's one way to interpret that. But what happens if we have the opposite? Instead, what if V1 is less than V2? What happens? Right? Obviously, if V1 is less than V2, then my current is going to be less than 0, right? And then what does it mean? Well, it means that we initially chose the direction of the current that was incorrect. We choose the incorrect direction of the current. We are getting a negative current, so the current, instead of flowing in this direction, is actually flowing in this direction because V2 has more power than V1. And the direction of its current is going to prevail over the other one, okay? That's what it means. So that's going to be the direction of your current if V1 is going to be greater than V2. That's one example. Let's take a look at another example, another simple one, too. But now this example involves 2 loops and 2 junctions. Do you see that here? 2 loops. Actually, we have 3 loops. I'm going to show you how exactly it works, okay? But we're going to have 2 junctions. Okay. So let's serve a very good example for you to understand how Kirchhoff's loop law can be used. Okay. So let's identify what are the loops. Okay, here you go. 3 loops. I'm gonna put a step by step here. Here you go. I'm going to first loop, right? Loop number 1. And I'm going to erase the currents as well. Oh, no. So the drawing is not too busy. Okay, we start. Oh, I want this one here. That's the first slide. I'm going to erase this. Oh, wait a minute. Yeah, we did this one, right? Yeah. That's the circuit. Find the current through the circuit, okay? We start by recognizing the loops. I don't need that anymore. Okay, R1, R2, R3, V1, V2, right? Identify the first loop. Identify the second loop. And then identify the third loop. That's here. And I'm going to go identify the third loop. I'm going to just erase those currents here. Ooh. And then you choose whatever direction you want for your current. In this specific case, I chose these directions for the current, right? Current from the left to the right in this branch, downwards in this other one, and downwards on coming from the V2. And then we are going to solve that, but I want to take a break right now, and I want you to think how you're going to solve this circuit as well. Find the currents I1, I2, and I3, okay? That's what we want to do. So I see you shortly in 15 minutes. Okay, I'm back here with 11:15 right now. We'll try to finish it in less than 20 minutes. So finish this example in less than 20 minutes so you can go for the quiz, right? So he go, oh, this one. Let's see here. Yeah, he go. Okay, okay, so he go, we're gonna go here. Okay, so we identify it. Here's the circuit. Okay, here's the circuit. We identify the first loop. We identify the second loop. And then we identify the third loop that goes on the outside. And then we identify the junction. There is one junction here, and then there's another junction here. Okay. Let me put another junction capital A and junction capital B. Junction capital A. Junction capital A and junction capital B. Okay. And if you're going to use junction B, the current looks just like that. Okay, the I1 here is the same as the I1 here that enters this point. The I2 is something that goes upwards here to be consistent with the R2 that is on the other side. Okay. Okay, that's the I2. And the I3 is a current that goes right here. This current I3 is the same as this one because it's in a single branch, right? This current here is the same as this one because it's in the same branch. And this current here is the same as this one because it is in the same branch. Okay. So what's happening here? Current coming from I2, current coming from I1 gets to point A and is split into I3. Okay, I2, yeah, I2 doesn't go anywhere, right? And it combines this I3 actually. I2 combines with I1 to give like I3. That's what this thing is all about. And here we have I3 coming here at this junction, and it's split into I1 and I2. Okay, what you have to know about very important about Kirchhoff's law, okay? In the above circuit, we identified 3 loops and 2 junctions. In order to solve a problem using this technique, you will need m-1 loops and n-1 junctions. Okay? Each of those loops generate an equation. Each of those junctions generate an equation, but you don't need all of them. You're going to need only 2 equations for the loop and just 1 equation for the junctions. That's because one of each equation of the loop / junction is dependent of the other equations, Okay. To solve, right? Not in order to solve a problem. So let's make things easier, right, for you. Just don't worry about all the 3 loops and the 2 junctions. Just worry about 2 of the loops and 1 of the junction. Put the equations together. You're going to have a system of equations. Let's do that loop number. Let's just concentrate on loops 1 and 2, right? And junction A. Loop 1. Okay, loop 1. We're going to start here from the left to the right. We are going from the region of higher potential to lower potential. So you have minus V2. Minus V2. Okay. Minus V2. You go across this wire that has no resistance whatsoever. And now you're going uphill against the current. Okay, and I'm gonna pass through the resistor. Usually we would get minus R1 I1, but because we are flowing against the current, we are gaining electric potential across the resistor. So instead of minus R1 I1, we write plus R1 I1. And that's because we chose the current in such a direction that we are going against the flow of the current. And then across the power supply V1, again, I'm going from positive to negative. It's going to be minus V1. $11.22. And finally, we go across resistor number 2, and we are going the same direction as the current. Consequently, we are going to lose electric potential. It's going to be minus R2 I1. Minus R2 I2, sorry. Let's see here. R2, yeah, R2. And don't forget. That's the first equation. R2 I1, and we close the loop. We're going to do for loop number 2. Remember, we don't need to do for loop number 3. Okay, and then I'm going to do for junction number A. Okay, here you go. Here's the loop. We start here at this point. From negative to positive, we gain electric potential. So it's going to be plus V1. Okay. We go across the resistor, we lose electric potential, minus R1 I1. Okay. And then we go across the resistor 3, which is flowing in the same direction. The direction of the loop is flowing in the same direction as the current, and we have to lose, we lose electric potential. Let's see, 3 elements, right? 1, 2, 3 elements, yes. So we don't have this element, R3, I3. That's our second equation. And then we're going to have our loop junction A. Okay, I already told you what was this one, right? So what's happening here? How do you interpret this drawing, right? Well, you interpret this drawing the following way. The current, whatever is coming towards the, the point is going to be same sign. So it should be I1 plus I2. Okay. And whatever is leaving is going to be negative. Or you can even interpret it the following way. I1 is summing up with I2 to yield the I3, to result in the I3 current. Hopefully that's correct, right? I put, notice that I put a length here of I3 that's shorter than the other one, okay? But we're going to find out whether it's correct or not. That's not a problem, right? So the junction A is I3. It's going to be given by I3 equal to I1 plus I2, like that. Okay. Or you can say I1 plus I2 minus I3 equal to 0. That would be another way. We are, because current involve electric charges, what we did here was a statement of conservation of charges. The amount of charge that arrives here plus the amount of charge that arrives from this direction is the same amount of charge that departs this direction. That's how you interpret that. We do not need this equation because this equation is going to be exactly the same as this one. The amount of current that arrives point B, I3, must be equal to I2 plus I1, must be equal to the amount of charge that departs this point. So we see this equation is exactly the same as this one. Similarly, this third equation would be like a linear combination of the other two. That's why we didn't have to worry about the third equation. Now notice that what we have here is a system of 3 equations. This is a system. This is a system of 3 equations with 3 unknowns. I1, I2, and I3. Okay, you go. This is on 3 equations with 3 unknowns. Consequently, we can solve this. Consequently, we can solve this system. And now it's just a question of using the appropriate mathematical techniques to solve that. Okay, it's no longer physics. It becomes a mathematical problem. And I'm going to leave this for you to solve on your own. Okay, the way I suggest you to do would be first, eliminate I3. Eliminate I3 by substituting substituting the third equation into the second one. Yeah, I don't think I'm gonna have time to do that because our exam is gonna be in 7 minutes, right? But I'm going to give a little bit of okay. Okay, then you're left with two equations. You are left with two equations with two unknowns. And the unknowns are going to be now I1 and I2. I1 and I2. I2. Two unknowns. Okay. So once you have, that's going to be the two equations. I eliminate the first one, right? I'm going to just, that's the I3 here. Then you choose whether you eliminate I2 or I1. It's up to you. Then you solve for I2, okay? Solve for I2. I'm not going to do that because it's going to take time. 11:29 now. Okay, so for I2. So for I2, using either the second or the first equation, it's up to you. Using either equation. Say, equation 1 is easier. Either equation, say equation 1. Okay. Yeah, it's easier. This one's going to be easier because you have just one I2 here. Has less terms, right? Substitute this I2, this result, into the second equation. And solve for I1. For I1. Okay, that's how you do it. Now you have I1 in terms of the non-parameters. Okay. Then substitute, then you walk back. Substitute I1 in the equation for I2. Okay, in the equation for I2. 11:31, almost there. Finally, substitute I1 and I2 into the equation for I1, I3. I1 and I2 into the equation for I3. Okay, that's how you do it. Okay, 3 minutes for the quiz. Okay, what's the Kirchhoff rules all about? It's a technique that uses conservation of energy and conservation of charges to solve problems involving circuits. The conservation of energy of electric potential equations are the equations that are obtained from the loops, of the circuit. Okay, the equation of conservation of charge are the equations that are obtained from the junctions of the circuit. You will always need, and then you need, minus one of the equations of the loops, minus one of the equations of the junctions. Okay, so 11:33, we're almost there. I want to stop here, and 2 minutes to start the quiz. Okay.
Professor, will you
Yes.
upload today's notes before the quiz starts?
Yeah, let's see. Yeah, I'll do that right now.
Thank you.
Save it, save as. Yeah. Deals notes. It takes a long time. Okay, good. Okay, so let's place in there. Browse is P07 notes, okay?
All right.
7 notes. We didn't have time to change it. Should be week 01 to. I'm going to delete this one. And then I'm going home here. Physics notes. Old notes. Okay. Old notes. Don't forget, all of that is in the old notes already. Okay.
Okay. Thank you.
So it should be there. Let me see if I can change. Once to leave this way. $11:35, so the quiz should be available to you all. Let me stop sharing the screen. I assigned 15 minutes to everybody. And if you're done, you can leave. You don't have to wait. Labelus, are you there?
Yes, I'm there.
Okay.
Yes, I'm here.
Okay, thank you. Ashley, are you there?
Yes, I'm here.
Thank you.